distance that the wave travels divided by time. The distance that it travels, how far out the wave goes, is just my wavelength. The time is my period. So that's just the wavelength times 1 over the period, which is the wavelength times the frequency, which is this formula I have right over here. There is a relationship between angular frequency and frequency. Angular frequency is equal to 2 pi times the frequency. If you think about it, frequency is the number of cycles per second, and then you multiply times 2 pi radians per cycle, and you get radians per second. All right, so let's connect a couple of things here. Questions before we actually connect Hooke's law into the stuff that we were just into the vocab. I have some coil here. Sits in some equilibrium, we'll call that x is equal to 0. I attach a mass to it. I then pull the mass outwards, and I let go. I know that F is equal to ma. Now, the force acting on it, based on Hooke's law, is negative kx. Because I've defined x is equal to 0 as basically the equilibrium spot, that's why I can get away with my delta x here is my final position minus my initial position, which I've made 0. So I'm just dealing with x. And that's equal to the mass times the second derivative with respect to time of x. So I have a second order differential equation here. How many of you are in DiffyQ, differential equations? Not Calc 1, but generally taken same time as Calc 3 or just after? No one? It's okay, it's not necessary. So I need some function of x so that when I take the second derivative with respect to time, I basically have a negative version of itself, other than potentially some constant up front. But I need some function whose second derivative looks a lot like the initial function, except a negative. What function have you dealt with where you take a second derivative and you basically have a negative of what you started with? Is it like math?
Like E, I guess in calculus would be E.
Did you say E?
Like if you took E to the negative 1.
Oh, E. If you did E to the negative x, and you did the derivative, you'd have negative E to the negative x, and then you take the derivative of again, you'd end up with positive E to the negative x. So you basically second derivative ends up with itself, and then you get negative of itself.
Cosine.
Or, yeah, one of those. Now, I have in the past, I'm not going to subject you to it, I actually have started with the generic equation, something times cosine plus something times sine, and then a half hour later we simplify it down to just one of them. So we'll just cut straight to that. We'll just let x is equal to some number times the cosine of something times time. There's that omega again. That is indeed the angular frequency. So my first derivative with respect to time becomes a omega negative a omega sine of omega t. My second derivative, negative a omega squared cosine of omega t. So indeed, the second derivative is a negative of itself plus, times some constant up front, which we will deal with now. Plug into our Newton's law equation right there. So I have negative k times a cosine omega t equals, not erasing off, negative a omega squared cosine, I lost my m there, negative m, negative m a omega squared cosine omega t. Now let's cancel stuff out. If these two are indeed equal to each other, then it should not matter what the time is, so I can just, the coefficients up front need to be equal to each other. My negative signs go away. Matter of fact, a goes away. What I'm left with is that k is equal to m omega squared. And so k over m equals omega squared. And so omega is the square root of k over m. So if I have some spring with a spring constant k, in other words, a stiffness constant, the larger k is, the stiffer the spring is, I attach some mass to it and I pull it out and let go and have it oscillate back and forth on a frictionless surface, the angular frequency is the square root of k over m. I know that omega is equal to 2 pi times the regular frequency. And so frequency is equal to 1 over 2 pi times omega, which is just 1 over 2 pi times the square root of k over m. The period is just the reciprocal of the frequency, so that becomes 2 pi square root of m over k. Let's try to give some tangible piece to this. I have a lever that is spinning around counterclockwise. So this is just, it's basically like, think of a clock running backwards. Why counterclockwise? Because the math people decided to make that the positive angle direction. This rod here is spinning around at some angular speed of omega. If I look at a projection of this onto a horizontal axis here, so at this point it would project onto there. So basically this piece, as it's going around, goes through the middle and then back, basically oscillating back and forth. The frequency with which it oscillates back and forth is f, and the angular frequency technically is the number of radians that are passed as it goes back and forth. I haven't run into a situation where I could not use angular speed and angular frequency interchangeably. It's just philosophically different. So the projection onto this axis is basically how often it goes back and forth is the frequency. Our equation right there, where was it? Our equation right here, well, we have a formula for omega. The position at some time t is equal to the amplitude times the cosine of the square root of k over m times sine. The amplitude would be whatever the length of this rod is. In other words, it is how long the projection is when this rod is horizontal. What is the maximum distance right there? That would be a. All this is well and good, but let's do some numbers. 3 kilogram mass, I pull it out 7 meters, and I let go. We assume an ideal spring, it's not gonna interfere with itself, it's not like this thing's gonna get to a certain point and then crash like a slinky does, or a slinky does interfere with itself at some point. We assume this coil is long enough to handle it. Immediately, I have a formula here. X is equal to 7 meters times the cosine of omega t. Because that 7 meters is the maximum it is going to be displaced from equilibrium. Omega is the square root of k over m. Ooh, we do need to give you that information. I have not given you k. So let's give you some information that I take the spring, and it naturally hangs a distance of 4 meters. Add a 6 kilogram mass to it, and the spring stretches out to 8 meters. No, let's make it 10 meters. We did some of this when we were doing the bungee jumping problem. This is an equilibrium. It's not like I put the mass on it and let go and watch the thing bob up and down. I put the mass on it, I let it hang, make sure it's steady, and I take my hand away. If that's an equilibrium, the forces up equal to forces down. This is based upon the spring. The spring is pulling it upwards here. So this is k times, well, how far it stretched, which is 6 meters. The force down, 6 kilograms times 9.8 meters per second squared. It's the weight pulling down. So 6k is equal to 58.8 newtons. So divide both sides by 6, and you end up with 9.8 newtons per meter. So now we can go over here, same spring, I put it sideways, and this becomes the square root of 9.8 newtons per meter over the mass that I attached to it, which is 3 kilograms. One 1.847366298. And the real answer is
1.807392228.
You usually don't have to go out that far, but sure. What's missing?
Radian per second.
Yes. I got some of the numbers right. All right. So my formula now, I've now taken it down to x is equal to 7 meters times the cosine of 1.807 radians per second times time. I can now tell you the position of this no matter what time we're talking about here. So let's figure out velocity. That's my position. I established that as the positive direction. Matter of fact, I established it as a positive direction as soon as I put a positive 7 here. That's when I made that way positive. My velocity. Well, it's going to be 7 times 1.807, which is something magical. Oh, there we go.
That's right.
Negative. That would be meters times radians per second times the sine of 1.807 radians per second times time. Now what's a meter radian per second? It does simplify.
Linears. Oh, meters per second. What were you looking for?
What is a meter? Right here I have meter radians per second because I multiplied 7 meters times 1.807 radians per second. So what does that simplify into? You did say the answer at one point.
Meters per second?
Yeah, meters per second. So this is, so my velocity, negative 12.649 meters per second times the sine of 1.807 radians per second times time. My acceleration formula, well, we just take the derivative again, so I'm going to take this right here and multiply times 1.807. So negative 20-ish, 21.9.
22.86.
2.86 meters per second squared times the cosine of 1.807 radians per second times time. Questions to hear? Austin. What's the maximum speed? All right, let's do a conservation of energy. The only thing doing any work here is the spring, conservative force. And so let's do conservation of energy. So we have omega is 1.807 radians per second. We pull it out, we let go. It's all potential energy when I first start out. I let go, it gets converted into kinetic. And so we have this translation here. So I have 1/2, we'll just start with Ki plus Ui equals K final plus U final. Yeah, we haven't done it today. Come on, we can do this. Get ready. In unison, it'll be incredibly beautiful when you do this. What's the formula for kinetic energy?
1/2 mv squared.
Told you it'd be beautiful. 1/2 mass times V initial squared plus, what is the formula for potential energy in this case?
1/2 K delta X. Oh, wait. Never mind.
They almost had it. That's one of those where, are you stopping there? No, well, let's throw that one in there. What's the formula for potential energy? The one associated with the perfect ideal spring.
1/2 K squared.
Yeah, the squared. 1/2 K delta X officially, but since I went ahead and defined 0 where I did, we can get away with just X squared equals initial equals 1/2 mv final squared plus 1/2 K X final squared. What can we get rid of? What's 0?
X initial,
Which initial?
X, or no,
Now, X initial, that's when I pull it out to here and I let go.
So that's when the problem starts, not at rest. When you let go.
When it is at rest at that point.
So,
So
long
V-
initial,
So,
speed initial?
yeah, that's equal to 0. I'm establishing 0 for the energy problem. I'm establishing that at this point right here.
So initial is when you pull it out.
What?
We could have made initial some other spot, but I figured it's easiest. If you don't like initial and final, I know that total energy stays the same, so, it gets into notation that I want to use. At time is equal to 0, so this is at time equals 0. And this is time when at equilibrium. The energy got here is equal to the energy, well, everywhere. So it starts out all potential. There's no kinetic. It's not moving when I pull it out, and at the moment I let go, it's not moving, and then it starts to move. That potential, all this potential gets converted into kinetic. And that the kinetic, it's all kinetic when the potential is 0 over here, when that's 0. So I have 1/2 K, whatever the position happens to be. Oh, no, this was the maximum position. It's equal to 1/2 mass times my V, F max, squared. So 1/2 times K, which is erased. Well, K was 9.8. 9.8 times 7 squared equals 1/2 times my mass of 3 times V squared, or V max squared.
You got 12.65.
I was going to go for 12.649. I was basically going for that number right there. Rounding differences is why that's a 4.9 and this is a 5.0.
But it's the same.
Yeah, it should be the same.
So maximum speed is always, like the magnitude is, well, it's always amplitude times omega.
The amplitude of position times omega, yes. So you have two ways of getting the exact same answer. What's the maximum acceleration?
You get it
22.86.
Meters per second squared. Or, if you don't want to do it that way, well, I know the maximum acceleration is going to happen when my force is maximum. My force is maximum when I'm out here. At that point, I have K times X is equal to mass times acceleration. So my acceleration is K X over M. If I want maximum acceleration, I want maximum position. So this is 9.8 times 7 divided by 3, which better be somewhere close to 22.86 meters per second squared. Emphasizing that the stuff we have done still applies here. We just have an alternate route of getting to the exact same place. All right, questions to hear? Let's take that same spring, naturally hung down, I think it was 4 meters. I apply let's put the 3 kilogram mass on it vertically. how far is it going to stretch now? If K is 9.8 meters per second, sorry, wrong, 9.8 newtons per meter. How much will it stretch? Or how would you find it?
Was it 3 meters?
Pardon?
3 meters?
I hope so. All right, so I know it's an equilibrium. I know mg is equal to k delta x. So how far it will stretch in addition beyond that 4 meters, it's just going to be the weight divided by the spring constant, which should be 3 times 9.8 divided by 9.8, which is 3 meters. So that's 3 meters. I now pull this thing down 7 meters and I let go. Still a 3 kilogram mass, and I have pulled it down an additional 7 meters. What's the maximum speed? Well, we've gone through this before. Let's do it again. What are the forces acting on this? Yeah, it's getting ready to count. What are the forces acting on it?
Spring force.
I heard weight and spring force. Anything else? Either of them non-conservative. Therefore,
Conservation of energy.
yes. My initial kinetic energy plus my initial potential energy is equal to my final kinetic plus my final potential. I have, that's really not much better. That's even worse. This chalk. All right. We have the gravitational potential energy, and we have our spring potential energy is equal to K final plus UG final plus US final. You know the formula for kinetic energy in your sleep. Formula for gravitational potential energy when the acceleration of gravity is relatively constant.
mg.
So we have mgh initial plus the spring 1/2 k delta x initial squared equals all that but final 1/2 mv final squared plus mgh final plus 1/2 k delta x final squared. So I pulled it down there and I've let go, and I want to figure out where's the speed the fastest and what is the speed. What can I get rid of?
Initial velocity.
Are we starting this off from it being pulled down 7 meters?
7 meters beyond that 3 meters. So 7 meters from there it's being pulled down.
But does it
Where does it
start
start?
at the the first 7 meters? So it gets pulled down 3 meters, is that where it starts?
So 3 meters, so from its just natural hanging position, it gets pulled, stretched 3 meters just by this hanging here, and then I pull it down an additional 7 meters.
Okay.
All right, we know the mass, we know G. I used 9.8 before, so let's continue with, so that's where I use G is equal to 9.8. So I know mass, I know G, I know K. What's the initial height? Okay. Because Lawson says so. So I have, what's my initial position in terms of, what's the initial stretch? How far is the spring stretched from its just natural hanging position? We're starting the problem here. It's not 0. That spring definitely is stretched. 10. It's 10 meters from its natural, nothing on it position. So this is 1/2 times 9.8 times 10 squared equals 1/2 times 3 times v squared. I'm trying to find the value of v, plus 3 times 9.8 times this h final, plus 1/2 times 9.8 times x final squared. So I need some relationship between h, f, and x. When h is 0, x is 10. As x gets smaller, h gets bigger, so they are opposite each other. Since x is the distance from here to wherever the mass is, and h is the distance from here to wherever the mass is, I know that x plus h is equal to 10. So it comes down to, do I want to solve for h or solve for, do I want in terms of h or x? Let's do it in terms of, x. So this is 49. It's 1.5 v squared plus 29.4 times 10 minus x plus 4.9 x squared. So if 1.5 v squared equals 49 minus 294 plus 29.4x minus 4.9x squared.